going to present our assignment.
Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to everyone. My name is Siti Sarah Pasami. My matric card number is CE190250. So today I would like to share with you guys the introduction for our assignment. Isamah Berhad is investing in a new coconut oil purifying plant as part of its expansion goals. The new factory will be able to generate higher quality coconut oil that fulfills the exacting demands of international markets. The heating process is an important step in the refining of coconut oil. To guarantee that the oil is adequately purified, the temperature of the oil must be carefully maintained. The oil will be run if the temperature is too high, and purifying procedure will be ineffective if the temperature is too low. The controller created for this project will be utilized to regulate the temperature of the oil during the purifying process. Many industrial and manufacturing processes rely on the heating process. It is used to heat things so that they can be used to conduct a range of functions. Heating can be used to melt materials, evaporate liquids, or cook food. For this assignment, it needs to develop a controller for the heating process to fulfill the desired performance given by Pisang Tanduk Holding. To develop a controller for the heating process, we had identified the problem first. Secondly, we decide to choose the controller design. Third, we do manual calculation, first order plus date time. Next, we calculate PID parameter using Ziegler-Nichols tuning. Lastly, we do the simulation, which is a simulation tools in MATLAB to create a model of the system and implement the controller. The simulation helps to evaluate the performance of the controller and its ability to meet the specific requirement. For the final results, the simulation needs to be analyzed and the performance of the controller is evaluated. It is critical to compare the achieved performance to the specification, which include temperature standards, settling time, steady state inaccuracy, and operation line. Okay, that's all from me. Thank you. Before we start to our assignment, we had planned and proposed the strategy. So as you can see, this is the Gantt chart for our project. For study and research, we had done 13 June until 2 July, and then for software study, we had done from 2 until 3 July. Next is research complete within 1 day, which is 4 July until 5 July, and then we do the manual calculation for 6 July until 7 July, and then the manual calculation complete within 1 day, 8 July until 9 July, and then software development within 3 days from 10 until 13 July. Next is project complete 13 July until 14 July, and the final improvement from 14 until 15 July. We had the project report from 15 until 16 July. Okay, that's all from me.
Good day, Doctor. I am Sasmita Davanathan, Matrix CE 2053. Here I am going to present the methodology for this assignment. Okay, first start, and then we have to identify the problem. Okay, the problem for this assignment is to establish the heating process for the coconut oil purification process while meeting specific temperature specification and performance criteria. And then we decide the controller design. So here we decide our controller as a PID controller, and then we proceed with calculate first order plus that time, which is FOPDT, and then we calculate the PID parameter using a Ziegler-Nichols tuning, and then we proceed with the Simulink simulation, and then a transit accepted. So at this stage, if the simulation result indicates the system's transit response meet the desired performance criteria, which is overshoot, setting time, and steady state error. So we will proceed with the result and analysis, and the process will be end. If not, if the transient is response is not meet the criteria, we will be adding up the NT with up, and then we will continue with the simulation, and then will be result analysis, and the progress will be end.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Rizal Shakib bin Muhammad Mizani. My matrix number is CE190085. So for my part, I will present for PID. PID controller, which is for the manual calculation. So as you can see on the left, there is a graph that has been given. So we have temperature in Celsius and time in second. So we have a line S and M. For first calculation, we have to find the scale of X. So 20 millimeters equal to 500 seconds, which is 1 millimeters equal to 25 seconds. So, and then next, we have to find the scale Y, which is 17 millimeters equal to 500 Celsius, and 1 millimeters equal to 2.94 degrees Celsius. So this is a degree Celsius. And then for the third one, which is time delay, so the theta equal to 10 millimeters times 25 seconds, which is equal to 250 seconds. And then we have to find the line between S, and M, which is S is 2000 Celsius plus 11 millimeters times 2.9 degrees Celsius equal to 231.90 degrees Celsius. And then for the M equal to 500 Celsius, 500 Celsius times minus 8 millimeters times 2.9 degrees Celsius equal to 26.8 degrees Celsius. For A, S and M, for the line between S and M, so we have to minus between S and M. So 231.99 degrees Celsius minus 26.8 degrees Celsius equal to 205.1 degrees Celsius. Then next, we have output response, which is 63.2% output response. So for the output response, we have to calculate by 63.2% times 205.1, which is A, plus M, which is 26.8 degrees Celsius. So we got 156.42 degrees Celsius. For the next one, 35 millimeters times 25 seconds, which is 75 seconds, for K equal to 41.02. And then for the process gain, K equal to 41.02, time delay 250 seconds, and a time constant J 875 seconds. So for the FOPDT, which is KE in the power of minus ES divided by JS plus 1 equal to 41.02 power of E minus 250 seconds divided by 875 S plus 1. And then the next part, we have a PID gain, Ziegler-Nichols tuning. So this is the formula for Ziegler-Nichols. And then for the KP, we got 0.1023891. And then we have JI equal to 2 theta, which is theta is 250. So 2 times 250, which is 500. And then for the KI, we got 0.00020477782. And then for the TD, 0.5 theta, which is theta is 250. So 0.5 times 250, which is 125. So for the KD, we have to times by KP times TD times S, which is 0.1024 times 125, which is 12.79866375. And then for the last part is a robust PID gain. So we got TA equal to square root of TI times TD. So we got square root of 500 times 125, which is 250. And then we got 0. And then for the last answer, we got 0.004. So that's all from me. Thank you.
I'm going to continue my presentation by demonstrate task 2, which is PID circuit. Okay, here is our circuit. Okay, first of all is a set point. We set our set point as 150 and then continue by Kp, Ki and Kd value. We got this value by using single Nichols tuning method. So the Kp value is 0.1023891 and then our Ki value is 0.0002047782 and our Kd value is 12.798637 and then here is our FOPDT. So the FOPDT transfer function is 41.02 per 875 S plus 1 and then here is our initial temperature which is 27 and then we run this. So we set our time the 5000. So this is our output graph. Okay, first of all we have to measure the settling time. So for 2% band settling time we have to uh, do calculation as 2 divided by 100 and times by our set point which is 150. So we will get as our 3 as our answer and then we have to find the upper boundary and the lower boundary. So the formula is the set point f to plus with 3 for the upper boundary and the set point minus with 3 for the lower boundary. So the upper boundary will be 153 and lower boundary will be 147. So here we have to set our horizontal line at 147 and 153. So I'll set our line here first. Okay. So here is our line. So then and then I have to measure the settling time. So the settling time will be around 2000 okay 2828. So here is the settling time and then we continue by finding the rise time. To find the rise time for the maximum we have to calculate as 90 divided by 100 times by our set point which is 150. We will get our maximum will be 135 and then minimum we will be divide 10 divided by 100 and times by our set point which is 150. We will get our minimum will be 15. So here we have to set that. So here is 15 and here is 135. 15 so 135. So yes, we can see that our rise time will be 120 seconds and then we continue by finding our overshoot. So the overshoot formula will be maximum overshoot minus set point divided by set point times 100%. So for in this case we have to enable the peak finder. Okay, so here we can see that our maximum uh, maximum will be 101.775 exponent positive 02. So which will be 177.5 our maximum overshoot and we will minus that with 150 and divided by 150 and times by 100%. So we will get our overshoot as 18.333%. Okay, for the analysis we can see that our temperature set point is 150 and the settling time 2% band is 2. We will get as 200 2828, and then our overshoot will be 18.333%, and the rise time is 120, and then our steady state error is 0. So we can compare that we didn't meet the desired specification. To get the desired specification, okay, for this analysis, we can see that our temperature set point is 150 degrees Celsius, and the settling time 2% band is we got as our 2828, and our overshoot is 18.333 percentage, and our rise time is 120 seconds, and we got the steady state error as 0. So in this case, we can see that our overshoot and setting time does not meet the given specification. So to solve this, we will be continuing by adding NT up. So my next groupmate will be present the demonstration by adding the NT up. So that's all from me. Thank you.
Good day, Doctor. I'm Gogleshwaran. So today I will present a demonstration on task 3, which is robust PID design. So robust PID design is mainly to provide stable and accurate control in the presence of uncertainties, disturbances, and variations in the system dynamics. So it aims to improve the system performance, robustness, and adaptability compared to the basic PID algorithm, which assumes an idealized model of the control system. So this is the PID circuit design for a robust PID circuit design, which already have done in the MATLAB. So this is the circuit. So when I run the circuit, I will obtain a graph like this. So this is the output for the robust PID circuit based on our parameters. So next is the settling time. So by adjusting the upper boundary limits here and the lower boundary limits there, we can obtain the settling time. So next is the rise time, where based on here we can see that rise time for the maximum is 19 over 100, 90 percentage over 100 times by 150, we will obtain 135, and for the minimum we will obtain 15 here respectively. And next for the peak time, so this is the peak time of the graph. So next for the overall overshoot percentage, we will get 5.333 percentage. So based on the maximum overshoot minus by the set point and divided by the set point. So this is the output for the robust PID circuit performance. So the settling time of 916.829 seconds indicates the time for the system to reach and stay within the 2% of the set point temperature. So the relatively short settling time shows fast and stable response. So the 5.33% overshoot suggests a minimal temperature deviation beyond the set point. So a rise time of 120 seconds indicates a quick response to set point changes. And the steady state of error of 0 implies the precise control and accurate temperature maintenance. So overall, the PID circuit performs robustly with short settling time, and there's a low overshoot, quick rise time, and a 0 steady state error. So next, for the comparison of PID circuit performance versus the robust PID circuit performance. So the robust PID circuit has a significantly shorter settling time, 916.829 seconds, compared to the PID circuit, which is 2828 seconds, demonstrating a faster stabilization and a tighter control. So the robust PID circuit exhibits a lower overshoot 5.33% compared to the PID circuit which is 18.33%, so leading to improved control performance. So both circuits have the same rise time of 120 seconds, representing the speed of response from 10% to 90% of the set point temperature. And both circuits also have a steady state error of 0, so which both circuits is maintaining a desired set point temperature. And next is comparison of design specification versus process variable for robust PID. So the robust PID meets the overshoot requirement best, which is should be less than 6%, with an overshoot of 5.333%. It also meets the setting time requirement, which is should be below 1650 seconds, with a setting time of 916.829 seconds. So additionally, it meets the steady state error requirement, which it should be less than 1.5 power to the 10 of -4, with steady state error of 0. So from here we can say that the robust PID circuit successfully achieves the desired specifications, demonstrating lower overshoot, shorter settling time, and zero steady state error. And its additive and compensatory mechanism enhance control performance, accuracy, and robustness. Thank you.
Hello, Assalamualaikum. My name is Syamil Bakri bin Ibrahim. My metric card is C190170. So today I would like to present about this assignment from subject PCS Process Control System. I'm from Group 3. So today I would like to present about task 4, which is document preparation and conclusion. So for our assignment, as you can see, so for our assignment, as you can see, this is the document preparation that I would like to explain. So this is document preparation that I have done. So as you can see here, I have done the flow chart for the document preparation. So first thing first, you need to do the project conception and implementation. So it goes to the definition and planning. So in below definition and planning, we have like plan, aim, scope, resources, and schedule. Okay, all those things needs to do under the definition and planning. Okay, so below from these five item, which is plan, aim, scope, resources, and schedule, we have approval. And then we have adjust or readjust. So if adjust, we continue to implementation, or if we need to readjust, we just need to definition and planning. We need to do the definition and planning again. Okay, so after the approval, we need to do the implementation, and then it continues to assign the task, and then continue by monitor progress, and then close. Okay, for below under the close, which here we divide by evaluation and documentation. Okay, we need to do this evaluation, documentation, and then archive. So that is our document preparation for this assignment. Okay, I have done the flow chart here. So it's called like project management. Okay, so I will be going to continue for the conclusion. So the conclusion for our group project is, in conclusion, it is crucial to develop a controller for the heating process in the pisang tanduk holding system to maintain quality and efficiency. A well-designed controller accurately regulates temperature, ensuring precise control and preventing adverse effects on pisang tanduk quality. Developing an effective controller involves considering system modeling, control strategy selection, sensor accuracy, and continuous monitoring. By addressing this aspect, the desired performance can be achieved, and the heating process optimized for the pisang tanduk holding system. So that's all for my part. Thank you.